Hello and welcome to lecture 22 of our Essentials of Semiconductor Device Physics course. In this lecture we're going to calculate the concentration of holes. Okay, so last time we obtained the number of free electrons, in other words, the number of electrons in the conduction band using the concept of density of states, which actually should be called density of orbitals. So we did that by taking the number of orbitals within an energy range. So this term is the number of orbitals within this energy range. So we take this number of orbitals and multiply it by the probability of each orbital to be occupied. So this entire product gives the number of occupied orbitals within this energy range. In other words, it gives the number of free electrons within this energy range. So all we need to do to obtain the total number of free electrons is to integrate over all energies of the conduction band. Then we divide by the volume and get the concentration of free electrons. Now this time we're going to follow the same logic to obtain the number of holes, in other words, the number of unoccupied orbitals in the valence band. So we build the integral in the same way we built the integral for free electrons. This term is the probability of an orbital to be occupied by a hole, in the same way that this term is the probability of an orbital to be occupied by an electron. And this term is the number of orbitals within the energy range. So this term is the density of states in the valence band. So to differentiate the density of states in the conduction band from the density of states in the valence band, I'm using the index H here for holes. So when we integrate over all energies of the valence band, so starting from minus infinity all the way to the highest energy of the valence band, which we call epsilon v, we obtain the number of holes, in other words, the number of unoccupied orbitals in the valence band. Okay, so let's begin by finding the probability of an orbital to be occupied by a hole. Since a hole is an unoccupied orbital in the valence band, then the probability of an orbital to be occupied by a hole is identical to the probability of an orbital to be unoccupied by an electron. Since the probability of the orbital to be occupied by an electron plus the probability of an orbital to be unoccupied by an electron must be 1 because the orbital must be either occupied or unoccupied, it follows that the probability of finding an orbital unoccupied by an electron, in other words, the probability of finding it occupied by a hole, is given by 1 minus the Fermi-Dirac distribution. So using the expression for the Fermi-Dirac distribution, then we can manipulate it a bit and we get this expression for the probability of an orbital to be occupied by a hole. Now we multiply the numerator and the denominator by this exponential. Notice that this exponential is the same as this, but with these terms exchanged. So here we have energy minus the Fermi level, and here we have Fermi level minus the energy. So this exponential times this must be 1. This exponential times 1 is the exponential. This exponential times this must be 1. So we have this expression for the probability of an orbital to be occupied by a hole. It's instructive to compare the expression we obtain with the expression for the Fermi-Dirac distribution. So notice that they are almost identical. The only difference is that in the Fermi-Dirac distribution we have energy minus Fermi level, and here we have Fermi level minus energy. So then we can use the same approximation we discussed in the previous lecture to obtain a simplified version of the probability of an orbital to be occupied by a hole. Next, we need to adapt the expression for the density of states in the conduction band to obtain an expression for the density of states in the valence band. So recall that this term is the effective mass of free electrons. So we need to replace this term with the effective mass of holes. In other words, the effective mass of electrons in the valence band. And also recall that this term is actually the radius in a plot of the natural numbers indexing each orbitals. So this must always be a positive number. So this radius is measured with respect to the reference energy epsilon c. Now our reference energy is epsilon v, and all energies now are lower than epsilon v. So we have to make sure to adapt this expression to keep this term positive under the square root, because it is a measure of a radius, and a radius is always positive. So doing these two modifications, we replace this term with the effective mass of holes, and we replace this term with the distance between the energy and the reference energy, but now take into account that the reference energy is the highest energy. So all energies in the valence band are lower than epsilon v. So this term here inside the square root is guaranteed to be positive, as we need it. So we have an expression for the probability of an orbital to be occupied by a hole. We have an expression for the density of states in the valence band. So all we need to do is to integrate over all energies in the valence band. So we start the integration from minus infinity all the way to the top of the valence band. So this is the full expression using these two functions. Now that we know how to build the integral, it's just a matter of looking up in a table how to solve it. So I'm just gonna quote the result here. And notice that this result is very similar to the one we obtained for the number of free electrons. But now we have the exponential here involving the highest energy of the valence band. Then we can get this result and divide by the volume to obtain the concentration of holes. In other words, the concentration of unoccupied orbitals in the valence band, which we express in terms of this ND parameter, which must be defined like this for the concentration of holes. Okay, so now we have an expression for the concentration of free electrons, and we have an expression for the concentration of holes. Notice that these two parameters, they are very similar. The only difference between them is the effective masses. So when the effective masses are the same, these two parameters are the same, but the effective masses are usually different because the way electrons interact with the underlying atomic structure depends on whether the electrons are in the conduction or in the valence band. So the effective mass of free electrons can be different, and usually it is different from the effective mass of holes. And as I mentioned earlier, these two expressions, they are very, very important to the physics of semiconductor devices. And notice once again that the concentration of free electrons increases with the Fermi level, in other words, with the chemical potential, but the concentration of holes decreases with the Fermi level. And that's because a hole is an absence of an electron. So notice the difference between the arguments of the exponentials. So now all we need to do to obtain the concentrations is to locate where is the Fermi level. And that's exactly what we're going to do in the next time. See you there.